Today we have a problem on thermal expansion, and in the scenario today we'll be considering a system of three rods where two of the rods are alike. We have rods X, X, and the one different is Y. These three rods are riveted at a strong constraint, and let us say the initial length is L0. It is important to note that the initial strain on each of the rod is 0. Also, we are given with the coefficient of thermal expansions for the rods X and Y. And we are given with the Young's modulus for both of the rods as well. Right. We have the entire system at some temperature theta is being heated to a final temperature of theta plus d theta. Right. So we have a change of d theta. So we are heating the entire system by some d theta, and coefficient of thermal expansion for the second rod, the rod Y, is greater than the X rod. Right. So we'll be solving this problem conventionally, and let us call the small change in length of X as delta Lx. This will have a magnitude of L0 times alpha x times d theta. Similarly, for Y we have L0 times alpha y d theta. So we have the change in length due to the thermal expansions, and we need to find the final length of the entire composite system. Right. Okay. Now let us reimagine the post-expansion situation here, and we have the figure. Let us call this end to be fixed. The left end is fixed and the right rivet is moving. So we call this change in length for the rivet as delta L. So we have the base of the expansion as delta L now after the expansion. Now we know that due to thermal expansion we'll have some extended length for X, so we have delta Lx, and same for Y as well. Y will extend more though due to the greater coefficient of expansion written over here. We had this information earlier. An important observation is that the force exerted along the rod X will be in the rightward direction, but that won't be the case for the rod Y. Due to the excess expansion will have a normal reaction which will oppose this new expansion. So we know that the stress for Y has to be equal to 2 times the stress for X, since we are having two rods of X, so that will be equated to the stress for Y. Now the stress is the Young's modulus of Y times the strain of Y, and will be 2 times the Young's modulus for X times strain for X. Now for the strain of X, we have the relative change in length, that is delta L minus del Lx by the original length, and the strain for Y as delta Ly minus delta L over the original length L0. Now solving this is a tedious part, so we get Young's modulus of Y times L0 alpha Y d theta minus delta L over L0, and that has to be equal to 2 times the Young's modulus of X times delta L minus L naught alpha y d theta over L naught. So we have this relation which will hold true for the entire composite system. So here we need to find the value for delta L, right? I'm not going to solve this, I'm just going to write the answer here. So arithmetically it can be solved. So we have the value for delta L as alpha y times the Young's modulus of y plus 2 times alpha x y of x by Young's modulus of y plus 2 times Young's modulus of x multiplied by d theta L naught. So we have this final change in length for the entire composite system. It can be inferred from the diagram, from the post expansion diagram as well. Also, when we talk about the final length of the entire system, we have the final length as LF, let us say. So we have L naught plus delta L. So we'll have this quantity over here. And then it was just calculations. So we are done with the question, and that brings us to the end of the video, and thank you for your time.